Valence electrons. So when we say valence electrons, we're referring to the electrons that are in the outermost principal energy level. We think of valence electrons when we talk about the main group elements. And so the group number corresponds to the number of valence electrons for all the elements in that group. Electrons that are not valence electrons are called core electrons. They're on the inside. So valence is on the outside, core is on the inside. And the number of valence electrons is something that greatly affects how the particular element interacts chemically with other things, and also some of its physical properties. So it's a very important idea. So here, if we look at main group elements in the first three periods, hydrogen, lithium, sodium, they're all in group 1A. They all have one valence electron. Their electron configurations end with what's here. So 1s1, 2s1, 3s1. Let's jump over here and look at fluorine and chlorine. They're in group 7A in the periodic table. They have 7 valence electrons. The electron configuration ends in 2s2, 2p5 for fluorine. So 2 is the highest level, highest principal level that has electrons. All the electrons in that level are counted as valence electrons. So we've got 2 in the S sublevel and 5 in the P sublevel. 2 plus 5 is 7. Chlorine also has 7 valence electrons, but its valence electrons are in the third level, not the second level. But fluorine and chlorine have very similar properties because they have the same number of valence electrons. And if we look at the noble gases, neon and argon both have 8 valence electrons. Helium up here is kind of the baby brother, just like hydrogen's the baby brother of all the elements. Helium is this, younger sibling of the noble gases. Helium has a full valence shell. The valence shell would be that highest shell. The first energy level can only hold 2 electrons. So it's full even though it doesn't have 8. So let's write an electron configuration for phosphorus and identify the valence electrons and the core electrons. So first we have to ask ourselves, well, how many electrons does phosphorus have? 15. So it's got 15 electrons. 15 electrons. So how do we write an electron configuration? No dots involved. Numbers and letters. 1s, and that 1s can hold how many? 2. And then next is 2s, and that can hold 2. And what's after that? 2p. The p can hold 6. So we're up to 10 electrons now. What's after 2p? 3s. So we put 2 in there. That's 12 electrons. We need 3 more. 3p, 3. And we're going to get to how we can figure this out just by looking at the periodic table. We haven't gotten there yet. So if we add up all these superscripts, 2 plus 2 plus 6 plus 3 plus 2, that gives us 15 electrons. As we look at this electron configuration, these are the principal energy levels, 1, 2, and 3. And so all of the electrons in that third level are the valence electrons. So how many valence electrons are there? 5.
Why are those the valence electrons?
The valence electrons, what we call valence electrons is defined as the number of electrons in the highest level, principal level. Yeah. Yes?
The letters indicate the shapes of the way they spin around the atom?
Yeah. The s orbital is spherical. The p orbitals are kind of lobe-shaped, like 2 balloons attached. And then the d orbitals were really crazy shapes. And then the f orbitals are just make your head hurt shapes. Yeah, so we looked at those. And S and P, you should know the shapes of. We run into those a lot. If you go on to organic chemistry, it's really important to be able to draw S and P orbitals. So we've got 5 valence electrons. Everything that's not a valence electron, these are the core electrons. So how many core electrons are there? 10. Okay, any questions?
What was the last thing you said?
The electrons that are not valence electrons are core electrons, that part?
Would it always be the last two?
It will not always be the last two. What you're looking for in the electron configuration is the highest large number. So, we've got these full-size numbers and then we've got the superscripts. Don't look at the superscripts for now. Here we've got some electrons in principal quantum level 1, and we've got some in 2, and we've got some in 3. There aren't any in 4. 3 is the highest level. If we go back to the quantum hotel idea, we're looking at what's the highest floor in the hotel that has people staying on it. The people on the highest floor are the valence electrons. Okay?
Because they get crazy.
I don't, we could make up all kinds of crazy things. When the tornado comes and takes up the top of the hotel, those are the ones that are going to lose their lives. I don't know. It's a fantasy land. We can make up whatever we want.
Sky bridge.
You can build a sky bridge, yeah.
Sky bridge that they built from one hotel to the other, and then they're covalent.
Ooh,
Just the one ceremony in the beds.
that.
It's volatile.
Maybe we
Tornadoes.
can bring someone over and go somewhere else.
Okay, those are some good ideas. Let's go on. Okay, let's learn how we can get all this information just from the periodic table. So the periodic table can be divided into 4 different blocks that represent the 4 quantum sublevels, S, P, D, and F. The group number tells us the number of valence electrons for that element. The row number tells us the highest principal quantum number that has electrons in it. So let's look at this. So here we have a nice color-coded periodic table. These first 2 columns represent the S block elements. So let's think about, hydrogen. Hydrogen has 1 electron. Where's that electron going to be? It's going to be in the 1s sublevel. So this is 1s1. And lithium has how many electrons? 3. So the first 2 electrons go 1s, and see helium kind of belongs over here right now. There's 1s2, and then the third electron is in the 2s. And this beryllium is 2s2. And if we look at rubidium, its electron configuration ends in 5s1. So it's kind of like a grid, right? Almost like you're playing bingo or something. And so we have, this is S1, and this is S2. And then over here, this would be P1, P2, P3, etc. So for calcium, calcium's in the 4th period. The 4 corresponds to the 4th quantum level. So its electron configuration ends in 4s, and it's the 2nd row, so this is 4s2. Let's jump over here to the pink ones. Those are the P block. So how many electrons fit in the P sublevel? 6. How many columns are there? 6. That's not a coincidence. So as we're going from beryllium with 4 electrons to boron with 5, that 5th electron goes into the 2p1. And this would be 2p2, 2p3, p4, p5, p6. Then that level's full. And we come over here and we've got the 3rd level, and we start with S1 and S2, and then it jumps to the P. Is this making any sense? P is filling 1 through 6, and then it goes to 4s. And then remember how there was this splitting of the energies and things got all kind of misordered, right? And it was confusing, and we had to come up with ways to remember what the order was. So the yellow here is the D block. The D block is 10 columns because the D sublevel can hold 10 electrons. But this isn't 4D. This is 3D. Remember, because things got a little out of order. I envision this part of the periodic table as having sunk down a level. So I imagine that it was supposed to be up here. Doesn't that make sense? We've got, you know, these nice little steps coming down, and then this would be 3D. But because of that interaction that we have, the energies of these sunk down. And so they're not in the, they don't seem to be in the correct order. But this is 4S, and then we go to the 3D level. And we fill up the 3D level, and then this part is regular, and this is 4P, and then we come to 5S, and then this is 4D. So all of those D blocks, that's the period number minus 1. That's their quantum number. And we'll find for the F block, it's the period number minus 2. So we go across here, this is filling up the 4D, then we come to 5P, 1 through 6. We come to 6S. We come to 5D, and then there's this little gap here, right? And notice the numbers, there's a disconnect. 57 to 72, something's missing. Those guys are down here. On this periodic table, to make it fit on the wall, they actually cut it and displayed it the way it really should be displayed, where you've got 56, 57, 58, you've got things going across in numerical order. We don't do this normally because it doesn't fit on a piece of paper very well. It's way too long for a regular piece of paper. And we don't use these F block elements much. A lot of them are man-made and radioactive, and so they just kind of stick them at the bottom, kind of like a footnote. But you jump from here, I'm back over on the screen now. You jump from here down to here. This is the F block. There's 14 columns there. There's 14 electrons that fit in the F block, F sublevel. So we go across, and this is 5D. It comes from, 4F. Oh my goodness. So it looks like it belongs in this 6th period, right? But for the F, it's the period number minus 2. So 6 minus 2 is 4. So this is 4F filling up, and then we jump back and we continue filling up the 5D, and then we come to the 6P, and then the 7S. You get 1 electron in the 6D, and then it jumps in and fills up the 5F. And then it goes and continues in the 6D. So that order from looking at the diagram or from doing the thing with the arrows, we can read off the periodic table. So, yes?
Can you do the previous example just looking at this?
Yeah, it was phosphorus.
Yeah.
So if we want to look at phosphorus and identify what its electron configuration is, I can look at phosphorus right here. Let me put a box around it. And it's really easy to do the noble gas configuration. I'm just going to look and see what's the previous noble gas. That would be neon. So I'll put neon in brackets. And then I'm going to write in everything that phosphorus has that neon doesn't. So it's going to be 3s2. And then I come over here, 1, 2, 3, 3p3. If I need to write the whole thing, this is 1s, there's 2. So 1s2, and then this is 2, this is the p, this is s, 2s2. And then we come over here, this is 2p, there's 6 there. I come over here, 3s, 2, and I continue on, and it's going to be a long day. 3p3. Isn't that easier? Did you know all that was hiding on the periodic table this whole time?
So they knew what they were doing, I guess. All that there.
They didn't. So the comment is they knew what they were doing. So they didn't know what they were doing. So the periodic table was set up like this based on observations of repeating properties in the elements. Didn't know what electrons were at that point. And then, we learned more and more and more. But the quantum mechanical model and the idea of these orbitals and sublevels didn't come around until the early 20th century. And lo and behold, these blocks correspond exactly to the number of electrons in each of these sublevels. It's not a coincidence. The quantum mechanical model explains why we put the periodic table together that way. We put it together based on a law, the periodic law, just observation of what we see without understanding. And quantum mechanics comes around and explains it. Yeah.
Is Schrodinger's cat experiment where they get the same curiosity killed the cat?
Actually, no, I don't think it is. Curiosity killed the cat because cats are curious, and that curiosity puts them in dangerous situations. You might also say curiosity killed the little boy, but that wouldn't be very politically correct.
No. Bad images.
Yeah.
I heard that the guy who came up with the periodic table, that it came to him in a vision in a dream or something.
I don't know. So the comment is that he heard that the guy who put the periodic table together, I'm assuming that would be Mendeleev, that it came to him in a dream. I haven't heard that. I haven't looked into the history of all that because I have very little spare time. It would be really interesting, though. I could see that happening, though, because a lot of times what happens is we've got a puzzle, right? Something we're trying to figure out, and we work on it, and we work on it, and we can't make any progress. And you go to sleep, and your brain keeps working on it. That's why sometimes you'll get answers to things when you're doing something else. Because if you let your brain kind of go fuzzy, right, and pay attention to something else, it keeps working, and then all of a sudden it says, hey, here it is. And so that's entirely possible. It's entirely possible. Yes?
Why don't you go to one P6? Like, why does it jump straight to 2 P6?
There is no p orbital in the first energy level, and that has to do with the quantum numbers.
Okay.
So for n equals 1, L can only equal 0.
Okay.
And so there's only one sublevel. And the second level only has S and P sublevels. It does not have a D sublevel. Good questions. So like if we were looking at chlorine, the inner electron configuration would be neon, and then the outer, or the valence electrons, would be these, the 3s2, the 3p5. That's a total of 7 valence electrons for chlorine. What if we were looking at bromine? Bromine is right below chlorine. So bromine would be, is that argon? Argon here. Bromine would have an inner electron configuration of argon, and then the valence electrons, what would those be? Oops. So we'd have argon, 4s2, 3d10, and then 4p5, right? These 3d10 electrons, are those valence electrons? No.
The fours
Only the 4s. Only the highest quantum number. So the highest quantum number here is 4. So the electrons in the 4th level are the valence electrons. These d electrons are in the 3rd level. This level filled after the 4s, but the 3ds are not considered valence electrons. And so bromine also has 7 valence electrons. Okay? Use the periodic table to determine the electron configuration of bismuth. And here's a periodic table on the slide for our convenience. Bismuth is right down here. So we're going to do the whole thing. So what's it start with? 1s2, and then 2s2, 2p6. All right, so this is 1s2, 2s2, 2p6, and then we've got 3s2, and then 3p6. And what's after that? 4s2, and then 3d10, because here's 4s, and then this is the D block. So we've got 10 in there, and that's 3, because that's sunk down. 3d10, 4p6, yeah, 5s2, so we're coming along here, 5s2, and then this is 4d10, and then 5p6, 6s2, and then things get a little wonky here. So here's lanthanum would be, this block would represent what?
F.
No, that would be.
It's still D. So this would be the 5D1, but then we jump down in here to the Fs, and the F is full. And so if we look, well, let's go back to this other one. Do you see how they wrote these? We write the 5D after the 4F because most of the 5D get filled before. I'm sorry,
How come we have 5D in the sun, but not in all of them?
well, we'll get to that. But when we have both of these, I lost it, like this one, we're going to write 4F first, and then we're going to write 5D, because most of the 5Ds are filling after the 4Fs. So when I'm going from 6S here, 6S, and I'm going to say, okay, well, this guy's, yeah, technically 5D, but he's going to be with all the rest of these guys, and this one comes first. So 4F, 14. And then 5D, 10. And now we're over here. We've got 1, 2, 3 in this P block, and that's 6P. 6P3. Yes?
How does this pertain to chemistry?
How does this pertain to chemistry?
Is it useful, like, if you're a quantum scientist, perhaps?
Well, the valence electrons, the concept of valence electrons is critical to chemistry. Yeah. And understanding how the electrons are arranged and why different things have the number of valence electrons that they have. So any questions about how to do that?
Still on the lanthanide, but the question I had earlier.
Yeah, we'll get to that. There's a thing about that. So how do you learn how to do this? How do you get good at it? You practice. Okay? You can do homework problems. You can go back and do the ones we've done in lecture, but you can also just pick a random element and practice writing out the electron configuration. And you can look them up and check your work. Yes?
What's the difference in directions when it says, like, do the electron configuration, so it's the big long one? What would it say if it wanted you to do the shorthand version, like picking the gas that comes before?
That would be the noble gas configuration.
Okay.
Yeah. So the noble gas electron configuration is always going to be shorter. Let's do that for bismuth. So the noble gas that immediately precedes bismuth is xenon. So xenon. And xenon goes up to 5p6, right? So all of this is the electron configuration of xenon. So by writing the element symbol xenon in brackets, we're saying all of that junk. And then we just need to write what comes after that, 6s2, 4f14, 5d10, 6p3. And I'm not going to try to trick you on an exam. So if it says, what's the electron configuration, or choose the correct electron configuration, it will either be noble gas, correct, one correct and a bunch of incorrect, or it will be the full-blown one. And I'm not going to try to trick you on that. How many valence electrons does bismuth have? 5. So the 6 is the highest principal quantum number. So there's 2 in the S and 3 in the P. 2 plus 3 is 5. You can get it from the electron configuration, but you can also get it from the group number. Group number 5A, bismuth is in 5A, it's got 5 valence electrons. Now, there are some irregular electron configurations. So the reason that the 4s sublevel fills first before the 3d is because of the interactions between electrons. And so the sublevels get split. But the difference in energy between those two levels is not very large. Especially in the transition metals, we'll see irregular filling for some of the elements. And what will happen is the NS, say the 5s level, will only be partly full, and then there's 4d electrons also. And these irregularities, we find them experimentally, and then we can kind of make up some excuses for them, or some reasoning behind it, but you can't just flat out predict which ones. And I'm not going to take you to task on these either, but I think it's important to understand that they exist. So if we look at chromium, this is the expected electron configuration for chromium. It's argon, and there's 6 more electrons, and we would expect them, 2 of them to be in the 4s and 4 of them to be in the 3d. But when we observe and do experiments, we find that there's actually 1 in the 4s and 5 in the 3d. One of those electrons has moved from the 4s to the 3d. Why? A question or an answer?
Perhaps it makes it easier to react.
Well, it has to do with energy. Okay? So how many electrons can be in an S sublevel? 2. So this is half full. And how many can be in the D sublevel? 10. So this is half full. So in my quantum hotel, this is like one of those Groupon deals, right? If you have 2 rooms that are half full of people, you get a discount. There's just weird combinations of things, and you get a discount. So there's a discount if those 2 sublevels are half full. And so the electron moves up. It's just more energetically favorable. For copper, we would expect 4s2, 3d9. What we see is 4s1, 3d10. So here 1 moves up, and now we have this D level completely full, and the S level half full. There's kind of a bonus when you have half full or completely full. We see a similar pattern for molybdenum and ruthenium. Well, ruthenium's just flat out weird. Why 4d7? I don't know. Because we've studied it, and that's what it does. Yes?
So what's the explanation for it jumps out of the S orbital then and goes to the D?
Well, the 4s and the 3d sublevels are very close in energy. It's not a big leap for it to go from the 4s to the 3d. And when you have this situation, you have 5 parallel spin electrons in the D sublevel. And so there's some stabilization in that compared to having 4 and 2. If you think of it in terms of the quantum hotel, in this arrangement, all 6 of these electrons get their own bed, right? Nobody has to sleep with another electron. It's like, okay, we can see the advantage in that, right? Would you pay a smidge extra for that? Sure. Like if it was 50 cents a night more, you'd totally do that. So instead of doing this, it does that. Yeah.
And the ones on the left exist.
Yeah, I think the ones on the left could exist, but that's not the ground state that we observe. It's what we would expect, but it's not what we observe. Yeah.
But for the next one for copper, how does it make it, on the right, how does it make that more stable when, like, because it went from 4s2 to 4s1.
Yeah, so no, this one's half full and that one's full. Right, so I can't, at this level, I can't explain it fully.
But is it because like, it went from, it's better to be full and kind of full to half full and completely full?
This one's full, this one's 9/10 full.
Yeah.
Here we have this one half full and this one completely full. Half full, completely empty. Those are like desirable states. So when we do this, now we have a completely full and a half full. And that's better than a completely full and a 9/10 full. That's a very simplistic explanation, but I think it's the best we can do at this level, yeah.
On the last one, why is there a 5s0?
Well, that's a good question. So here we've got 5s2, 4d8. So this one has gone so that we've got one that's empty and one that's completely full. And that apparently is better. I mean, if you just moved one up, you'd have one that's half full and one that's 9/10 full. And it's like the hotel set these weird, quotas or something, or you're playing a video game and you have to collect this, this, and this, and if you have that too, then you get a bonus. That's the best I can
I
do.
believe Ruthie was kind of like,
Yeah. So when we see the your question about the D and the Fs and why would some of them, let's go back to that slide. If we look down here, this one is 4F1, 5D1, and then this one goes to 4F3. Why didn't that one stay in the D orbital? Well, the 5D and the 4F orbitals are really, really close in energy. And so they shuffle around more. We don't see that happening up here where the difference in energy levels is greater. But as you go higher and higher in energy, the energy levels get more and more closely spaced. And so then we get more and more irregularities.
so the F just stole the electron from D?
You could think of it that way. Or, it just didn't like that room and wanted to go stay in the other room with his buddies.
And that's the same reason with the number 64, GD. That's the same
Yeah,
reason it stays at
gadolinium.
7 and has 1 on the D.
Yeah, see now this one, 4F7, that's going to be exactly half full. But then here, we take that 5D and it goes back to the 4F. And so there are irregularities in filling. And you definitely do not need to know any of those down there. I want you to know that that happens and not to be bothered by it. I think it's a good idea to at least know chromium and copper, that they're bizarre, because that could show up on an exam. But that's sort of an A student thing. If you're an A student, you should pay attention to that. If you're B student or below, then just writing electron configurations is good enough, because that'll at most be one question on an exam.